We are continuing in section 4.2, and in this section we'll be looking at voltage dividers and power equations for series circuits. The voltage drops in a circuit are proportional to the resistance value. So what that's saying is that the voltage drops that we will experience in a given circuit are going to be proportional to the values of resistance in that circuit. The voltage divider equation is very useful in determining the relationships in a series circuit. And so here we have an equation we're solving for V, we're calling this X, this is going to be what we're solving for. In this case, we're going to be solving for R1, so we'll be solving what is the voltage drop across R1. And this is the formula, Rx, in the case this will be R1, divided by the total resistance times the applied voltage. And in this case here we have R1. R1 is 10K, and the total resistance, if we add up these 10, 20 plus 30, it will be 60. And if we solve this, we could say, what we say, 10 divided by 60 times 120. And in this case, we can look at this and see that this is simply the 10 over 60 is going to be 1/6. If you want to get a calculator, you could, but we'll just say 1/6 of 120 is going to be, 20 volts? Probably about like this. We'll probably have a 20 volt drop here. And let's jump to the next slide. I have a prepared circuit for this. So we said this first one was 10 over 60 times 120, and that would be about 20 volts. And the next one here, 20K, again we could do the same thing, 20 divided by the total resistance, which is 60 times 120, and again this looks like 2 over 6, what's that, 1/3? About 1/3, and 1/3 times 120 would be about 40. And then we have the final one, R3, 30 over the total resistance of 60K times 120. And if we wanted to do if this is 1/2, you want to say 0.5, you could do that. You could say 1/2 and whatever, but it's going to be half of 120, which is about 60 volts. And so in this equation, we have a 20 volt drop here, a 40 volt drop here, and 60 here. And if we were to add these up, 60 plus 40 plus 20, guess what? 120 volts, and that equates to our applied voltage. In the previous section, we had looked at Kirchhoff's law, and what did Kirchhoff's law say? Well, it said that the applied voltage will equal the applied voltage. So the voltage applied to each of the individual components will equal the voltage source. So in this case, the voltage across the individual components equals the source voltage. Okay, power. Power in a resistive circuit can be thought of as heat dissipated by the resistors, and we measure power in a quantity called watts. And we talked about watts in earlier chapters. The more power dissipated, the hotter the resistor. Total power in a series circuit is determined by the sum of the individual power dissipation. So the total power will equal the sum of all the individual powers within the circuit, or all the individual power drops within the circuit. And so here we're looking at the same circuit again, and we're going to use our little calculator this time. We need to know what is the, in fact, let's step back just a moment. When we calculate power, I've got a couple different formulas we'll use in this particular screen. We'll look at current times resistance, and we'll also look at current squared times resistance. So first of all, if we're going to use this formula, we need to know what is the total current in the circuit. So we have our applied voltage is 120 volts, and we will divide that by the total resistance in the circuit to find what is the total current. So in this case we have 120 volts applied, and we will divide that by the total resistance, and the total resistance is 60 exponent 3, that would be 60K, and so we have our value of 2 milliamps, and that's what we show right here. Now the voltage drops in this particular circuit, we calculated them previously. R1 was 20 volts, R2 was 40, and R3 was 60. So if we wanted to calculate the drop across R1, or the power drop across R1, we could say current times voltage. So here we have our 2 milliamps times the voltage drop, which was 20, and that will equal 40 milliwatts. And so we could go to this component and document 40 milliwatts. And our next one, we could do the same thing. Let's go in and put in our value of 2 exponent minus 3, which is our 2 milliamps. And again, we would take that times the voltage drop on R2, which we previously calculated as being 40. So if we went times 40, and there should be no surprises here, 80 milliwatts. So let's document this component as having an 80 milliwatt drop. And on the final one, let's use our other formula. Let's use this formula down here. Let's clear our screen first. And let's do current squared times resistance. So again, we're going to go 2 exponent minus 3. And we'll take that, we'll square that. We have a function on our little calculator here for squaring that value. And then we'll take that times the total resistance, and in this case it is 30K. So we will say times 30 exponent 3, and we'll get 120 milliwatts. So here we have our final calculation here, and if we were to sum these, we would say what, 40 plus 80 plus 120, and there should be no surprises here. Let's see, we get a 4, carry the 1, 240 million, or 240 milliwatts. Now one way to test our calculation, we could, in fact there's a number of ways we could test this, but we know that the total current in the circuit is 2 milliamps. We could use this to solve for the total current in the circuit. So in that case, we would say 2 milliamps exponent minus 3, and take that times 120. And again, should be no surprises here, 240 milliwatts. And we could use the same equation, I squared times R. We could do it that way. We could say clear 2 exponent minus 3, and let's see, let's square that value and then take it times, and what are we going to take, multiply it by? In this case we're looking for the total wattage, so we would take that times 60K, so times 60 exponent 3, and again 240 milliwatts. So we solve power in a couple different ways. Okay, this lesson we have looked at power in series circuits, and we looked at how the power is equal to the sum of all the drops. And we also looked at voltage divider calculations. We looked at the individual voltage drops across given components, and we found that the voltage drop was proportional to the resistance of the total circuit times the applied voltage. This concludes this lesson.